Okay. Good afternoon, everyone. I'm Ravikrishna G. I'm working as assistant professor in E&C department, Vidyavartika College of Engineering in Mysore. Today, I'm going to discuss some of the concepts with some examples that is related to the electronic devices, which is pertaining to the GATE 2021. So, before moving on to the sample examples, let's move on to the syllabus that you need to be ready for the exam. The syllabus for this electronics devices is looking like this. Here, basically, in this particular section, you need to understand what exactly the energy band in intrinsic and the extrinsic semiconductors, which means you should have some thorough knowledge about the conduction band, valence band, and the Fermi level and its variation under equilibrium condition and under forward bias or under reverse bias voltages and under equilibrium condition. In addition to that, you need to understand the equilibrium carrier concentration and the direct and indirect band gap semiconductors. Anyhow, this direct band gap and indirect band gap semiconductors is used to choose the material type for different types of the applications. Here, if you want to choose the materials for the optoelectronic devices, for examples, we need to consider the direct band gap semiconducting material. For the normal operation or for the normal applications, similar to your switching applications and the amplifications, we need to go for the indirect band gap semiconductors. Any of the examples for this direct band gap semiconductors will be the compounded semiconductors, whereas the examples for your indirect band gap semiconductors will be the silicon germanium. Okay. Here, the next we need to understand the different types of the carrier transport. Next, we need to understand the different types of the carrier transports. Okay. Here, there are two types of the carrier transport. These are the transport mechanisms. The one carrier transport mechanism is the diffusion, and another one is a drift. Which means basically there are two types of the conduction mechanisms that are possible. Okay. One is the conduction mechanisms in the semiconductors will be, one is due to the diffusion. And another conduction mechanism is due to the drift. Here, this diffusion mechanism, you are going to encounter this diffusion current conduction mechanism due to the concentration gradient. Whereas we are going to encounter this drift current mechanism due to potential gradient. Here, concentration gradient means, for example, if you consider the PN junction that is under equilibrium, that is without applying any voltage across its terminals. So because of the majority charge carriers on the p type, that is the holes, and the majority charge carriers on the n side. Here they are going to diffuse from the higher concentration region to the lower concentration region, whereas this drift mechanism. Okay, any of the during this diffusion process, because the charge carriers are moving, that leads to the current. Okay, so that leads to the diffusion current. So the second type of the mechanism is the drift mechanism. Here, whenever we apply the potential across the terminals of the particular device, the current is going to flow. So that's why it is known as the drift mechanism, which means here we need to apply the potential across its terminals to make the current to flow in the particular device. To make the current to flow in that particular device, we need to apply the potential difference. So the corresponding current mechanism is known as the drift current mechanism, whereas whenever there is a concentration gradient in that particular device, then the current that is going to be constituted is known as the diffusion current mechanism. And again, we need to understand the mobility and the resistivity in that particular device or materials. Next, we need to understand the generation and the recombination of the carriers. That is known as the electron hole pair generation and the recombination process. Next thing is the Poisson's and the continuity equation. Anyhow, these are the very basics. These are the basics that you should have. So before going to the next stage, that is the devices, first you should be aware of these concepts. That is, you should be aware of the energy bands in both the intrinsic semiconductor and the extrinsic semiconductor, and you need to understand which are all the carrier concentrations that are available in that particular device. And in addition to that, after understanding the charge carriers or the concentration of the charge carriers in that particular device, we need to understand which are all the current mechanisms that are possible in that particular device. Once if you understand all these basic concepts, then we can move on to the actual devices. That is the PN junction. This is basically a two-terminal device. The Zener diode, this is also a two-terminal device. This is going to operate in the reverse breakdown region, whereas the PN junction is going to operate in the forward biased region, or the forward region, and the reverse biased region, or forward bias condition, or in the reverse bias condition. Whereas the Zener diode, which is going to be operated in the breakdown region. Later on, we need to focus on the three-terminal devices known as the BJT and the MOSFET. Anyhow, the art for this particular MOSFET is going to be the MOS capacitor. Most of the times, you may expect the questions from this MOS type. That is the MOSFET as well as the MOS capacitor, which means most of the times they ask the questions on the MOS capacitor as well as on the MOSFET, because nowadays the trending device is the MOSFET. Nowadays, the trending device in any of the integrated circuit is your MOSFET. So it is better to know the basic operation of this MOSFET and what exactly the MOS capacitor is going to be. The next is the electronic, that is light-related devices, that is known as your LED, photodiode, and solar cell. Okay, in order to understand all this stuff, these things you should understand. That is energy bands, carrier concentration, carrier transport, that is diffusion and drift current mechanism, and the associated mobility and resistivity of that particular carriers. And of course, in between, we need to focus on the Poisson and the continuity equation. And of course, these equations are used to solve the electric field within that particular device. And most of the times, usually, most of the questions were asked only from this PN junction, BJT, and the MOSFET. However, you may focus on these concepts also, but the majority of the questions you can expect from the MOS, BJT, and the PN junction. Okay. Now, quickly, let's move on to the examples that were asked in your previous GATE examination. Okay, so this is a question that was asked in one of the GATE examination in ECE paper. You just look at this question. A small percentage of the impurity is added into an intrinsic semiconductor, at 300 Kelvin. So which one of the following statements is true for the energy band diagram that is shown in the following figure? It is given that the energy band diagram is given like this. This is your valence band and this is the conduction band. Here, band gap of this particular energy band diagram. This is the band gap energy EG. And within this EG, the energy level is one energy level is introduced in this particular EG. So here we need to take some conclusion from this particular diagram. Here, a small percentage of impurity is added to the intrinsic semiconductor at 300 degree Kelvin or 300 Kelvin. Which one of the following statements is true for this particular energy band diagram? So let's move on to the options. So before moving on to the options, we need to understand one thing. So whenever impurity atoms is added, whenever an impurity atom is added into the semiconducting material, it introduces the energy level. It introduces the energy level within the band gap. Okay, that we have seen in the above figure. But actually, if you just carefully observe this figure, the energy level, that is the introduced energy level, is nearer to the conduction band. Here, the energy level that is introduced within this band gap is nearer to the conduction band. So, for this particular case, we need to get some conclusion. So, see here impurity means basically we know that we can add the donor atoms, or the impurity can be the donor atoms or the acceptor atoms. It can be donor atoms or acceptor atoms. If we add the impurity, that is, if we add the donor atoms into this semiconducting material, or if we add the donor atoms into the intrinsic semiconducting material, what happens? That leads to N-type material. If we add the acceptor atoms into the intrinsic semiconducting material, then that leads to the P-type semiconductor. Usually, whenever these donor atoms are introduced into the intrinsic semiconductor, the energy level will be introduced in the band gap. The energy level known as the donor energy level will be introduced within the energy band gap, and this donor energy level will be nearer to the conduction band. It is nearer to the conduction band. Now, if we dope this intrinsic semiconductor with the acceptor atoms, then that leads to P-type semiconducting material, that is extrinsic semiconductor. So in this particular case, the energy level will be introduced. But where exactly the energy level will be introduced? The energy level known as acceptor energy level will be introduced in the energy band gap, which is nearer to the valence band. Now just look over this particular diagram. From this particular, we need to get some conclusion from this. See here, go to the first option here. In the first option, here the intrinsic semiconductor is doped with the pentavalent atoms to form the N-type semiconductors. You just look at this statement here. Okay, we have introduced the impurity atoms, and if this impurity atom introduces the energy level that is nearer to the conduction band, that leads to the N-type semiconductor, right? If you just look at this energy level, this newly introduced energy level in the energy gap is nearer to the conduction band, which means the energy level, the new energy level in this figure, the new energy level is nearer to the conduction band. This is your conduction band. So which means, so which type of extrinsic material it will be? It will be of N-type semiconductor. Okay, since the newly introduced energy level is nearer to the conduction band, this leads to the N-type semiconductor. Okay. So the third option and the fourth option will be not possible, because it is leading to the P-type semiconductor, which means they have given that whenever we introduce the energy impurity atom, that leads to the energy level which is nearer to the conduction band, but that is not possible in the case of P-type semiconductor. But because in the P-type semiconductor, what happens here, the introduced energy level in the band gap will be nearer to the valence band, but this energy level is not nearer to the valence band. It is nearer to just a 0.01 electron, because if you just look at the intrinsic semiconductor for the silicon, what happens, the energy band gap will be around 1.12 electron volt, right? So what happens here, you just look at the new energy level that is introduced here. This energy difference is just only 0.01 electron volt, that is from the conduction band, which means this is very, very nearer to the conduction band. So it can be either A or it can be B. Now let's look on to the option A and B. Okay, intrinsic. Okay, this leads to the intrinsic semiconductor that is doped with pentavalent atoms to form the n-type semiconductor. And the second option is intrinsic semiconductor that is doped with trivalent atoms to form the n-type semiconductor. Anyhow, here we already know that in order to form the n-type, we need to introduce the donor atoms, right? Whether the donor atoms are the pentavalent atoms or trivalent atoms, definitely the donor atoms are the pentavalent atoms. Then only they are going to introduce, one electron, or they are going to donate one electron. If we dope the acceptor atoms, that doesn't leads to the n-type semiconductor, that leads to the p-type semiconductor, which means here acceptors are of trivalent atoms. Okay, these acceptor atoms are of trivalent atoms. So the option B is not possible. So the correct option for this particular case is option A. The correct option is option A, that is intrinsic semiconductor, which is doped with pentavalent atoms to form the n-type semiconductors. Here it is very simple. First, identify the newly introduced energy level. Now observe whether that introduced energy level is nearer to the conduction band or which is nearer to the valence band. If it is nearer to the conduction band, that is going to be your donor energy level. Since here this is nearer to the conduction band, that is the bottom of the conduction band, this is your donor energy level. For example, if they ask you the same question, but if they introduce the energy level nearer to the valence band, then that leads to p-type semiconductor. Okay, that leads to p-type semiconductor. Just be careful about that. For example, if the same question can be asked in different ways. For example, if this is the diagram, for example, the possibility. Okay, here if this is the possibility, the possible question can be asked like this. This is the conduction band and this is the valence band. And if the newly introduced energy level is nearer to the newly introduced energy level is nearer to the valence band, then what it corresponds to? It corresponds to here the newly introduced energy level is nearer to the valence band, then that leads to the p-type semiconductor. So if it is a p-type semiconductor means, so which option will be correct? Then it should be either C or D. But here, in order to form the p-type semiconductor, we need to dope that silicon or intrinsic semiconductor with the trivalent atom. That is, D option will be correct. Okay, if this is the figure means the option D is correct. Option D is correct because the introduced energy level, the energy level that is introduced in the band gap is nearer to the valence band. Okay, so that is a p-type semiconductor which is having the acceptor atoms. Here the intrinsic semiconductor is doped with acceptor atoms. So now let's move on to the next question. Okay, so this is a very basic question. Okay, now let's move on to the next question. Okay, here this is again asked in your GATE exam. Here the figure shows the band diagram of the metal oxide semiconductor. Okay, metal oxide semiconductor, which means it is related to the MOS capacitor. Okay, or in general MOS capacitor. Here it is given that the surface region of this MOS is in. Okay, the question is, it is going to be the band diagram. This is going to be the metal. Okay, this region is the metal. This region is the metal, and this region is the oxide. This region is the oxide, and this region is the semiconductor. This region is the semiconductor. Okay, this region is the semiconductor. It is shown that in the metal, that only one energy level is shown, whereas in the oxide layer, the energy levels are not possible, so it is not shown here. And if we just look at this energy band diagram in the semiconductor, please observe carefully at the extreme side, that is at the extreme side as well as at the interface, because in the question he has asked about the surface region of this particular MOS is in. whether it is in the inversion or it is in the accumulation mode or it is in the depletion mode or it is in the flat band condition. So we need to identify that one. If you just carefully observe in the substrate or in the semiconductor, if you just look at this, here the Fermi level is nearer to the, here EFS represent Fermi level of the semiconductor. Okay, EFS corresponds to the Fermi level of the semiconductor. If you just observe this, this Fermi level is nearer to the conduction band. Here it is nearer to the conduction band, which means which type of material it should be of? Which means this is of substrate, right? This is usually the substrate region. Okay, this is usually your substrate region, because if I take the MOSFET here, this is your N plus, and this is your N plus, this is the oxide, and this is your metal. Usually nowadays this metal has been replaced by polysilicon. So if you consider this is going to be your substrate, right? This is nothing but your substrate or the semiconducting region. So if the Fermi level is nearer to the conduction band, which type of material it should be? So which type of material it should be? It should be of N-type material. It should be of N-type material. Okay, it should be of N-type material, because the Fermi level of this particular semiconductor is nearer to the conduction band. The Fermi level is nearer to the conduction band, that leads to the N-type semiconductor. So now let's move on to at the junction or at the interface between the oxide layer and the semiconducting region. This is the interface, or this is the surface region. Okay, they have asked that what happens here? What happens? It is in the accumulation, or it is in the depletion, or it is in the flat band mode. So in order to do that, see here, the surface region means, that is nothing but silicon dioxide and silicon interface. Okay, anyhow, this is also silicon, because this intrinsic silicon is doped with the donor atom, that leads to the N-type material. So the substrate is of N-type material. Now the surface region means that is nothing but the silicon oxide and silicon interface. Okay, at this interface we need to know what type of mode condition it is going to be valid. Now look at this. At this junction or at this interface, what happens here? Go to the Fermi level. This is your Fermi level. Okay, this dotted line is the Fermi level, and this is the intrinsic level, and this is the top of the valence band, and this is the bottom of the conduction band. Okay, whenever we join the two materials, definitely at the junction the band bending will happen. So that's why here the band bending is happened here. Okay, here band bending happened because the two different materials are joined together. Okay, because it is at this particular point the two materials are interconnected. So that's why your band bending is shown here. Okay, because of this, your this band is bended like this. So if you just look at this, see here, this dotted line, that is this horizontal line, is your Fermi level, and this is your valence, top of the valence band. So at the interface, or at this interface, what happened here? At the interface, what happens? The Fermi level is nearer to the conduction band, it is nearer to the valence band, right? That is, it is nearer to the top of the valence band. This is your top of the valence band, and this is your Fermi energy level. So it is, since the Fermi level is nearer to the valence band, so which type of material it should be, or which type of carriers you're going to get at this particular junction? Definitely it will be of p-type, right? Because for a p-type semiconductor, the Fermi level is nearer to the valence band, so it is of p-type. But earlier, what happens at this particular region, it is of n-type. But at the junction, what happened? It is converted into p-type, right? Which means, so what happened here? It is, so in which mode it is having? Which mode it is having at the interface? It is having the inversion mode at this interface, because it is converted from n-type to p-type, which means something is happened here. And of course, maybe due to the applied potential, the charge carriers, that is the minority carriers in this n-type material will be attracted towards this, and of course, so that's why your this Fermi level is nearer to your valence band. So what happened here? The inversion happened here. Okay, because of this inversion, that is from n-type to p-type, we need to call it as inversion mode at this junction. Okay, for example, if they bias in such a way that if this G is equal to 0, what happens here? If this phi b is equal to 0, then the work function or the bulk mode, for example, if it is of p-type, for example, in this particular case, at this end, for example, at the extreme case, if this Fermi level is nearer to the valence band, then that leads to p-type. And here, for example, this Fermi level is nearer to the conduction band. Here also the inversion is going to happen. Okay, so this is about the second question, and again this is based on the MOS capacitor. Okay, this is again the MOS or MOS capacitor. Now let's move on to the next problem, which is again based on the MOS capacitor only, because this is very important. This is the MOS capacitor. Okay. Okay. See here the two MOS capacitors were given. This is your figure A, and this is the figure 2. This is the figure 1. This is the figure 2. Here it is given that the figures 1 and figure 2 show two MOS capacitors of unit area, which means they are of the junction area, or the area of those two MOS capacitors will be same. And the capacitor in the figure A, this is the figure A, and the capacitor in the figure A has the insulating materials of type X and Y, which means here for this particular MOS capacitor, it is having the insulating materials. X of thickness T1 is equal to this is the X material. Some dielectric. Okay, some dielectric material of thickness T1 is equal to 1 nanometer. And the dielectric constant is given as 4. And the dielectric constant of this dielectric material is given as 4. And it is also having one more insulator above this. One more dielectric material is also available over this, and whose type is of Y type. Which means this dielectric material and this dielectric material are of different types. And here the dielectric constant or the dielectric constant of this Y material or Y dielectric material is 20, and it is having the thickness of T2, which is equal to 3 nanometers. T2 is equal to 3 nanometers and dielectric constant of 20. Now come to the second figure. Here this is also a MOS capacitor, but here instead of having the two dielectrics, we are having only one type of the dielectric. Here in this figure 2, it is having only one insulator of type of material type X, which means this material as well as this material are same here. It means it is also of X type. Okay, this is of dielectric type X, whose dielectric constant is same as 4. Okay, because for this particular material, the dielectric constant will remain same. But here the thickness of this particular dielectric material is given as TEQ. That is, TEQ is the thickness of this dielectric material. So here what we have to do is, if both the capacitor, that is if the capacitors are of equal capacitance, which means the capacitance of this MOS capacitor as well as the capacitance of this MOS capacitor are both same, or of having same value, then we need to determine the thickness of this dielectric material in nanometers. That is the question. So here what we can do is, remember the first capacitor. Okay, here if you just look at the first figure, I'll just call it as the capacitor C1. Okay, the capacitance that is associated with this MOS capacitor is C1, and the capacitance that is associated with this MOS capacitor is C2. Okay, C2. Now let's move on to the first capacitor type. Here, what happens here? See here, there are two dielectric materials are there, right? One is of X type and another one is of Y type. So what is the equivalent capacitance? What is the equivalent capacitance due to these two different materials? The equivalent capacitance due to these two materials will be will be COX1 into COX2. That is oxide capacitance, because here these two capacitors will be in series here. Okay, here these two capacitances will be in series, so that's why we need to write C0x1 into C0x2 divided by sum of the oxide capacitances, because here these are connected. So if one material is deposited over another material, the equivalent capacitance of this particular capacitor is going to be C0x into C0x2 divided by C0x1 plus C0x2. Now let us write this oxide capacitance in terms of the permittivities. Okay, in terms of the permittivity. So we know that C is equal to epsilon A divided by the thickness, right? Thickness of that particular dielectric material. See here in this particular case, this is a general way to express the capacitance. For this oxide capacitance, this is going to be oxide material, and we need to consider the thickness of the particular oxide here. Okay, here if you just consider, it is given that in the initial line only, it is given that it is having a unit area, so there is no need to bother about the area here. Okay, so here how we can write this oxide capacitance? This can be written as epsilon naught x, because area is 1. So what happens to the thickness? Thickness will be T naught x1. So into, now let's move on to the second oxide capacitance. So it will be epsilon x2 divided by thickness of the oxide 2, thickness of the second dielectric material, divided by epsilon naught x1 divided by T naught x1 plus epsilon naught x2 divided by T naught x2. Okay, but what is this? It can be written as, the permittivity is written as the relative permittivity of the oxide into permittivity of the crystals, right? So it is going to be written as epsilon naught into epsilon r. So what is epsilon r for this oxide layers? Epsilon r is given as, 4, and for this it is given as 20. Okay, so if you just substitute all these values, and if you write this in terms of epsilon naught and epsilon r, this will be epsilon naught into epsilon r1 divided by T naught x1 plus, I will just take the epsilon naught as constant, because for both the terms epsilon naught will be available. Plus, which it is epsilon naught into epsilon r1 divided by T naught x1 into epsilon naught into epsilon r2 divided by T naught x2. Divided by, again, here we need to consider the epsilon naught to be constant because of this plus sign. So it will be epsilon r1 divided by T naught x1 plus epsilon r2 divided by T naught x2. So this epsilon will cancel out. So the resultant will be epsilon naught into epsilon r1 epsilon r2 divided by, if you just simplify this, what happens? This will be epsilon r1 into T naught x2 plus epsilon r2 into T naught x1. Okay, if you just solve this, if you substitute everything and if you solve this, what happens? If you solve this, it will be epsilon. You just solve this, what happens? It will be it will be 80 by 32. Okay, it will be 80 by 32. Okay, this is the capacitance of this particular capacitor 1. So this is the equivalent capacitance of the capacitor 1. Okay, this is the equivalent capacitance of the capacitor 1. Okay, this is for capacitor 1. Now we need to consider the capacitor 2 also, right? because for both the capacitance 1 and capacitance 2, the value will be same. So now let's move on to the second capacitor. So here the capacitance value of this capacitance, I just call it as C equivalent of 2, which is equal to epsilon naught x, because of only one dielectric material that is available here, because only one dielectric material is available here. So I just consider only one oxide layer, that is epsilon naught x divided by T naught x. T naught x. But what is T naught x here? The T naught x is equal to TEQ. Epsilon naught x divided by TEQ. TEQ. But we need to equate this this total capacitance of this capacitor as well as this capacitor, right? So what we can do is, now I just equate the capacitance of the capacitor 1, that is 80 by 32, is equal to epsilon naught into epsilon r divided by TEQ. Because here for this oxide layer, it is made up of X type material, right? This is made up of X material. So what is the relative permittivity of that material X? What is the relative permittivity of the material X? The relative permittivity of the material X is given as 4. It is given as 4, which means that is going to be same as the previous case only. So if you just substitute epsilon naught and epsilon r, here epsilon naught is given. If it is not given also, sorry, here epsilon naught is not given, but usually the value will be 8.854 into 10 to the power minus 4, right? So if you just, okay, sorry, this is 80 into epsilon naught, right? Because they are just substituted only these values here. Okay, this will be 80 into epsilon naught divided by 32. So here this epsilon naught will cancel out. So the equivalent capacitance or the total capacitance or the total thickness of the capacitor 2 will be, TEQ will be epsilon r into 32 divided by 80. We know that the relative permittivity of the material X will be of value 4 into 32 divided by 80. So if you just solve this, you will get T equivalent, or the thickness of the second capacitor is equal to 1.6 nanometers. It is 1.6 nanometers. Okay. Here basically it is a here in this particular question, the options will not be given here. Okay. In I think you are aware of that scheme. I think so. Okay, there are different types of the questions you will be asked. One is of with the multiple choice questions, and the other type of the question known as NAT questions. In this particular case, you won't get any, they won't give any options here. So here, usually we need to find out that particular value, and we need to write down, or we need to enter with the help of the obtained values. Okay, here we have T equivalent is equal to 1.6 nanometers. Since it is already given that it is in nanometer, there is no need to write NM into 10 to the power of minus 9. This is sufficient. 1.6 is the correct answer. Okay. Now let's move on to the next question. This is again based on the PN junction. Okay, or in general some device. Okay, because any device is basically made up of the PN junction only. Any electronic device is basically made up of PN junctions. So we can consider this under the PN junction heading. Okay. So see here for this particular question, which one of the following options describes correctly the equilibrium band diagram at 300 Kelvin of a silicon PN N plus P double plus configuration? Here, see that whenever they write it is as N plus, it is known as highly doped N type material. Okay, this is the highly doped. It is the highly doped N type material. Highly doped or heavily doped semiconductor. Highly doped or heavily doped semiconductor, or heavily doped N type semiconductor. Okay, so if I write N double plus, it is very heavily doped material. It is again heavily doped material of heavily doped n-type material, where in which here the doping level in this particular case is greater than n plus, which means the doping, if you consider the doping levels, in n double plus, the doping levels will be more compared to the doping level in the n plus semiconductor region. Okay, if they represent only N or P, then usually we call it as the moderately doped semiconducting regions or semiconductor materials. Here see here, this is moderately doped semiconductor material. This is also moderately doped semiconductor, whereas this is your heavily doped N-type semiconducting material. Okay, this is heavily doped N-type semiconducting material, and of course the doping level of this N plus is greater than this N. And if you consider the extreme semiconductor material, that is this one, here it is represented as P plus plus, which means this is again heavily doped compared to this P. So here N plus is heavily doped compared with the N region. P double plus is heavily doped compared with the P type semiconductor region. Okay, P type semiconductor region. So you just carefully observe the question here. What they have asked is, we need to identify the correct representation of the energy band diagram for this particular device structure. This is some device. We don't know what exactly this particular device. They have just given the PN, N plus, P double plus device. In general, we call it as some device. Okay, this is some device. We don't know whether it is a MOSFET. We don't know that. Okay, it is some device which is having this doping concentration. Okay, this is Pn plus P double plus. We need to identify the correct representation of the energy band diagram under equilibrium condition. It means without any no biasing. It means under no bias condition. Under no bias condition, we need to identify the correct representation of the resultant energy band diagram of this particular device. Okay. Before that, let us consider some concepts here. So here we know that for N-type material, we know that the Fermi level, usually the Fermi level will be nearer to the conduction band. Whereas in the case of the P-type material, this is your EC, that is the bottom of the conduction band, and this is your EV. And in the case of the P-type material, the Fermi level will be nearer to the valence band. This is the Fermi level. Okay. Under equilibrium condition, whenever the two materials are joined together, under equilibrium condition, whenever the two materials are joined together, that is under no bias condition, usually the band bending will happen. Which means under equilibrium condition, the Fermi level will be constant. The Fermi level will be constant. See here also we need to consider the equilibrium condition, because it is given that we need to identify the correct energy band diagram for the particular structure under equilibrium condition, which means under equilibrium condition, the energy band diagram is going to be constant. The Fermi level in that particular energy band diagram will be constant. But if you just look at the figures, or if you just look at the options here, see here in the option A, okay, the Fermi level is constant. Okay, this may be right, but we don't know exactly. Let us see. Now let's move on to the option B. Here the Fermi level is not constant, because in the equilibrium condition, this Fermi level is not constant. It is varying, right? The Fermi level is varying like this, which means it is not at all possible. Okay, option B is not correct. Now let's move on to the option C. Here also in option C, the Fermi level, this is the dotted line. Okay, this Fermi level is varying under equilibrium condition, but that is not correct. Okay, that is not possible here. This Fermi level should not vary like this. It should remain constant under equilibrium condition. Okay, however, the Fermi level can vary, or it can bend only under biased conditions. So the option B and option C is not correct. Okay, just by looking at the figure, we can say that the Fermi level is not constant. So that's why we can say that option B and C is not at all possible. Okay, so the only left options will be option A, either option A or option D. Now let's look at the option A and option D. So before moving on to the option A and D, we need to know that in this particular case, you just observe this. This is the p-type semiconductor region, right? This is a p-type p double plus semiconductor region, and this is of p-type semiconductor region. See here, whenever we dope the semiconductor with the either acceptor atoms or the donor atoms heavily, usually what happens is the Fermi level will go deep inside the valence band, which means if I consider the heavily doped uh, p-type region, if I consider the heavily doped p-type semiconducting region, if I consider this heavily doped p-type semiconductor region, usually the Fermi level will be below valence band, will be below valence band. Whenever we dope heavily that particular p-type semiconductor or silicon material, usually the Fermi level, okay, if we moderately doped with the p-type material, or if we moderately dope with the acceptor atoms, then the Fermi level will be nearer to the valence band, which means just above the valence band. But if we dope this intrinsic semiconductor with p-type material heavily, or if we dope that particular semiconductor with the acceptor atoms heavily, then that Fermi level will move, or it will fall below the valence band. This thing we should keep it in our mind. Similarly, in the N case, for example, in this particular case, if that particular intrinsic semiconductor is heavily doped with the donor atom, then the Fermi level will be EF will be above the conduction band, will be above the conduction band. Okay, if you just look at this particular diagram here, in the option A, this is the Fermi level. Okay, look at the right extreme side. Look at the right extreme side, because we need to concentrate on the P double plus region. Okay, that is this region. This is your P region. This is the N region. This is N plus region, and this is P double plus region. So in this P double plus region, the semiconductor is heavily doped with acceptor atoms. So that's why here the Fermi level should fall below the valence band. Okay, here this is the top of the valence band, and this is your Fermi level, and this Fermi level move below the valence band. So that's why this option could be correct, because one thing is Fermi level is constant for all the, from this end to this end, from this end to this end, the Fermi level is constant. But and in the P double plus region, and in the P double plus semiconducting region, the Fermi level is below the valence band, that is top of the valence band. So this is correct. But in the, let us check for the case B also. Okay, one thing is under equilibrium condition, the Fermi level is constant. Okay, that is valid. But in this particular case, the Fermi level is above the valence band in the P double plus region, or in the heavily doped p-type material, the Fermi level is above the valence band. That is not correct actually. Okay, it is not actually correct. And because here, see the distance here, this distance is very large, or this energy difference is very large, and actually in this P double plus region, this Fermi level should fall below the valence band. Okay, so this option is also not correct. So the correct option is option A. Correct option is option A. So here we need to focus these 2 points. That is under equilibrium condition. Under equilibrium condition, that is under no bias condition, the Fermi level will be constant. Okay, under equilibrium condition, for this entire structure, that is from this end to this end, the Fermi level should be constant. Okay, whenever they ask you to determine the or understand the band diagrams of a particular device structure, means we should keep it in our mind that the Fermi level should be constant under equilibrium condition. Okay, under equilibrium condition, the Fermi level should be constant. The Fermi level should be constant. Okay, so, and another thing is, whenever this particular material or semiconductor is heavily doped, then that particular, since we are considering it as a p-type material, the Fermi level should fall below the valence band. Okay, it should fall below the valence band. Okay, So that we are observed in the KCA. Now let's move on to the next question. Let's move on to the next question. Okay. Here it is given that it is again based on the PN junction only. It is again, the question is based on the PN junction. If we just look at this question, it is given as consider a silicon PN junction with uniform accepted doping concentration, with uniform accepted doping concentration of 10 power 17 per cubic centimeter on the P side, and a uniform doping concentration of 10 power 16 per cubic centimeter on the N side. Okay, for example, if I consider a normal PN junction, I consider the PN junction or PN device. Okay, this is of P-type material and this is of N-type material, and this P-type is doped with the acceptor atoms, and the concentration of that acceptor atoms is given as 10 power 17 per cubic centimeter, and it is uniformly doped here. So here this region is doped with acceptor atoms of 10 power 17 per cubic centimeter. Okay, the concentration of the acceptor atoms should be of 10 power 17 per cubic centimeter. Now coming to the N-type region. In the N-type region, usually we need to dope the intrinsic semiconductor with the donor atoms, and whose donor concentration is given as, donor doping concentration is given as 10 to the power of 16 atoms, 10 power 16 donor atoms per cubic centimeter, Okay, so now here also it is given that the no external voltage is applied to the diode. Here the no external voltage is applied to the diode, that is, we have to consider the equilibrium condition. Which means the device is under equilibrium state. And it is given that Kt by Q, that is the thermal voltage, is given as 26 millivolts, and the intrinsic concentration of the semiconductor or intrinsic concentration of the silicon is given as 1.5 into 10 power 10 per cubic centimeter, and the permittivity of the silicon is given as 12 times epsilon naught, and the permittivity of the free space is also given here with the charge is equal to 1.6 into 10 power minus 19 coulombs. Here what we have to determine here is, and again this is of it doesn't have any multiple choice options. It doesn't have any options. You need to write out the answer here. Okay, we need to determine the charge per unit junction area in nanocoulomb per centimeter square in the depletion region on the P side. Okay, this is of NAT type question, and here it is given that we need to determine the charge per unit junction area in the depletion region. See here, whenever we consider the equilibrium PN junction, whenever we consider the PN junction under equilibrium condition, what happens? Because of the concentration gradient, the majority charge carriers will diffuse from its higher concentration region to lower concentration region. Okay, due to the concentration gradient, here the majority charge carriers, are the holes, and these majority charge carriers, that is the holes, will diffuse from the P side to the N side. Okay, they are going to diffuse in this direction. Similarly, holes diffuse in this direction. Similarly, in the N-type semiconductor bar, the electrons are the majority charge carriers, and these majority charge carriers will diffuse from the N side region to P side region. Why they are going to diffuse? Because of the concentration gradient. Because of the change in the concentration, they are going to diffuse. So here the electrons will diffuse from the N side to the P side. Okay, here because of this diffusion process, what happens here at the junction? We know that at the junction, immobile carriers will be, or immobile ions will be created at the junction. Okay, whenever we, for example, if you consider the neutral atom, if I remove the electron, what happens? If I remove the electron, and if I add the electron, to that particular atom, what happens if I remove the electron? It will be positively charged, right? The resultant atom will be positively charged. If I add the electron, the resultant atom will be negatively charged. Okay, because of this removal and addition of the electrons, so the ionization process is going to happen. And here also the same thing is happening here in the N region, in the N-type semiconductor region. Here what happens here? The electrons are moving from this region to this region, because the doping level is very nearer to the conduction band. And this temperature usually this temperature is 300 degree Kelvin, 300 Kelvin. Okay, for 300 Kelvin only we will get 26 millivolts. At 300 Kelvin, the electron that is available in the donor energy level will be excited from the donor energy level to the conduction band. Okay, and that conduction electron will be responsible for this movement. Okay, and that electron is responsible for the diffusion process here. Similarly, the holes also. Whereas in this particular case, in the p-type semiconductor region, acceptor energy level will be nearer to the valence band, and at 300 Kelvin, that particular hole, that is an empty state in the acceptor energy level, will be filled with the valence electron. Okay, so that's why the hole is going to be created again in the valence band. So due to this diffusion process, here the immobile ions will be created. That is, the positive ions will be created on the N side, the positive ions will be created on the N side, and the negative ions will be created on the P side. Okay, the negative ions will be created on the P side, and this leads to the depletion region. Okay, this is going to be your depletion region now. This is the depletion region. Okay. Okay, this is the depletion region, wherein which there are no mobile carriers are available. This is the depletion region. Okay, this is the depletion region. Okay, if I just consider this, see here, we need to determine the charge per unit junction area in the depletion region on the P side. Here, this is your P side, right? Which means we need to determine the charge per unit area in this P-type region of this particular depletion region. Okay, we need to consider the charge per unit junction area in the depletion region on the P side, that is this region. In this region, we need to determine the charge per unit area. So let us consider, or let us redraw this particular diagram one more time. This is your PN junction or PN device. This is your junction, and this is the depletion region. And here it will be of having the negative ions. Here it will be of positive ions. And by charge neutrality, whatever the amount of charge that is present on this side should be equal to this side. Okay. Otherwise, what happens? The further movement of the electrons or the hole, that is further movement of the majority charge carriers, is not going to be possible. That means, in simple terms, the charge neutrality should be maintained here. Okay, the density of the ions here should be equal to this number of ions. Okay, that charge should be same here on both the sides. Okay, if I consider this is the total width, of the depletion region, I just consider W as the total depletion width, and I just consider this as 0. It means I'm just considering along X direction. Okay, it is having only one direction. So I just consider this as depletion width on the N side, and this is the depletion width on the P side. That is, from year to year, it is having the depletion width of WP, and from year to year, it is having the depletion width of WN. Okay, where the total width is given as the WP plus WN. Here, we need to determine the charge per unit area, right? So in order to do that, we know that in order to calculate the charge here, either on the N side or on the P side, if I consider the P side, the total charge that is due to these ions is going to be written as the area, junction area. We need to write the charge on the P side is going to be the junction area into charge of the charge associated, and Since we are considering the p-type material, so the doping concentration, we need to consider the doping concentration. Since it is of p-type material, we need to consider the acceptor atoms. Okay, we need to consider the acceptor atoms concentration into the total depletion width on the p side. Similarly, if they ask you to calculate the charge per unit area on the n side, means, for example, okay, they may ask like this also. In this case, on the n side, we can write the charge on the n side. The charge on the n side, I will just write this as QP and this as QM. The charge on the n side is the total junction area into the charge Q into, since we are considering the n-type material here, it should be having the donor atom concentration. It should be of donor atom concentration into the depletion width value of Wn. Okay, into Wn. So here, anyhow, for this case, we need to consider this equation here. So here, what we have to do is Q divided by A. This we need to determine. But what is this Q by A? Q by A is written as Q into NaWp. So in order to calculate this, we need to remember some formulas that is known as the junction potential or the built-in potential, because this total width is going to be dependent on the built-in potential of this particular device. Okay, so here what I will do is, I will just consider the built-in potential of this particular junction. We know the built-in potential of this PN junction can be written as thermal voltage Kt by Q into ln, that is log base E, NaNd divided by Ni square. NaNd divided by Ni square. We here Ni is going to be the intrinsic carrier concentration in that particular silicon. Okay, this is the, which means if you consider the intrinsic semiconductor, we need to consider how many charges are available per cubic centimeter. It is already given that Ni is given as 1.5 into 10 to the power of 10 charge carriers per cubic centimeters. Here Na is also given and Nd is also given. So here the thermal voltage is also given. If you just substitute everything here, because Kt by Q is given here. Kt by Q is given. This is your uniform acceptor doping concentration, that is Na, and here this is your Nd. This is your Nd. Okay, Nd is equal to 10 to the power of 16 per cubic centimeter, and Na is equal to 10 to the power of 17 atoms per cubic centimeter. Okay, if you just substitute all this stuff, and here Ni is equal to 1.5 into 10 to the power of 10, and Kt by Q is equal to 26 millivolts, you will get. Okay, please substitute that, and because everything is known for us, and this is a log base E, okay, log. So if you just substitute all the values, you will get the built-in potential to be 0.757 volts. This is the built-in potential. With the help of this built-in potential, we need to calculate the total depletion width of that particular junction. Okay, now we need to calculate the total depletion width. This is the total depletion width. So here it is quite quantitative, which means we need to remember some of the equations here, where the depletion width is going to be obtained as, there is no shortcut for this. You need to remember 2 into epsilon divided by Q into 1 by Na plus 1 by Nd. That is 1 over acceptor concentration into, is 1 by NN, which is the 1 over acceptor concentration, acceptor atom concentration, as 1 over the donor into the concentration, into VBI, that is the built-in potential. Here it is given that the epsilon is given as, epsilon is also given right for us. The epsilon is also given, that is epsilon is equal to, here we need to consider, since we are considering the silicon material here, it is already given that this epsilon of that particular material is given as 12 into epsilon naught. And if you just substitute that, this is epsilon, means epsilon of the silicon. Okay, here epsilon of the silicon is given, Q is given, the acceptor concentration is given, the ND is given, VB we have found out here. If you just substitute it, if you substitute all the values here, substituting the values, we will get the value of the depletion width. That is the total depletion width we will get. The total depletion width here is 3.325 into 10 to the power of minus 6 centimeters. Okay, this is the total depletion width. This is the total depletion width of that particular depletion region. But actually what we have to calculate, the charge per unit area on the P side, semiconducting region. Okay, that is Q by U, this one. So in order to calculate this charge over area, we know the value of this Q, we know the acceptor concentration, but we don't know the value of this WP, right? But how to calculate this WP? We know that the depletion width on the P side region is equal to the concentration, that is the doping concentration on the N side, NA plus ND into the total depletion width, If you just substitute all these values here, and again, how did we obtain this? By simplification again. Because here, if you just simplify this W is equal to WP plus WL, you will get this equation, okay? Okay, here we need to write WP is equal to or in other way, we can write in other way also. But here let's follow this rule, that is ND into total width divided by NA plus ND. If we substitute all these values here, we will get some value here. Okay, here we are going to get the WP value, and if we calculate everything here we are going to calculate WP is equal to you just substitute this value as well as this value, because all these are known here. So if you just substitute this in the charge per unit area, you will get, because we know the charge per unit area is equal to Q into NA, into depletion width on the P side. So we know this one, and we know this one. Okay, so here this is nothing but this stuff, right? Or if you don't know anything, you can write the WP here itself. Here we can write the WP here itself. That is Q is equal to Q into NA into WP is equal to ND into W divided by NA plus ND. Because here we know the charge, value of this charge, we know the concentration of the acceptor atoms and the donor atoms, and we know the total depletion width. Okay, and we know the total depletion width. So from this, what we will get here is the total charge upon unit area will be equal to 4.836 nanocoulomb per centimeter square. Okay, and actually this is a 2 marks question, and you need to understand what exactly this built-in potential, and now actually this is related to the concentration of the acceptor atoms and the donor atoms. So here, the charge per unit junction area in the depletion region on the P side is given as, it is already given that it is in nanocoulomb per centimeter square. So we need to just write down the values here. So the value of that is 4.836. Okay, in some time they may ask only up to 2 decimals and up to 3 decimals. Okay, depending upon the question, we need to answer this one. Okay, if they ask only that up to 2 decimals, we need to answer only 4.83. If they mention to write up to 3 decimals, means it should be 4.836. Okay, yeah, because already the units are already given, so there is no need to write down again here. Okay, this is, we should not write like this into 10 to the power of minus 9. Okay, this is not correct because this nano is already available here. Okay, so the only answer is 4.836. Okay, now let's move on to the next question, which is based on the N-channel MOSFET. That is, it is based on the MOSFET. And this question is based on the MOSFET. You see here in the question, it is given as consider an N-channel MOSFET. Consider an N-channel MOSFET with a gate to source voltage of 1.8 volts. It is given as the gate to source voltage, that is VGS, is given as 1.8 volts. 1.8 volts. And it is given that the aspect ratio of the device, the aspect ratio, that is W by L, aspect ratio of the device is given as W by L is given as 4, and the mu N C naught X is given as 70 into 10 to the power of minus 6 ampere per volt square, and the threshold voltage of the device is given as 0.3 volts. 0.3 volts. And here one more parameter is given, that is the channel length modulation parameter, that is lambda, that is 0.09 per volt. Okay, you're going to see this channel length modulation effect in the saturation region here, basically. Okay, for example, if you consider the output characteristics of the MOSFET, N-channel MOSFET, this is your ID and this is your VDS. So here, for a particular VGS, up to the pinch off point, the ID is going to increase linearly. Later on, after reaching this particular pinch off point, the current is going to be constant ideally, but practically you won't get the constant current like this. Okay, there will be some slope will be there here. There will be some slope will be there, and there will be some slope here. But practically there will be some slope, and if you join all these points here on the left hand side, you are going to get the voltage as 1 by lambda. Okay, anyhow, just don't bother about all this theory part now. Okay, you are going to see this channel length modulation effect in the saturation region. So it is given that in the saturation region, the drain conductance, which means we need to determine the drain conductance. What is the drain conductance here? Here the drain conductance means 1 over drain resistance, that is 1 by RDS. Since it is given that the characteristic is not ideal, because they are already given the channel length modulation effect, they are already given the channel length modulation parameter as 0.09 per volt. So that's why definitely there will be a slope in the saturation region. Definitely there will be a slope in the saturation region. Okay, so here we need to determine this channel. We need to determine the drain conductance, and of course that is nothing but 1 over RDS. That is nothing but 1 over RDS. So how to do this? How to calculate? Here it is in the saturation, right? Which means you know that in the saturation region, this is nothing but what is this RDS here? RDS is nothing but 1 over slope here. RDS is equal to 1 over slope. Which means here GDS is nothing but slope. Yeah. But what is the slope here? Slope is equal to change in the y-axis divided by change in the x-axis. What is the change in the y-axis here? Here y-axis, in the y-axis we have written it as the drain current. So what is the change here? Change in the drain current divided by change in the x-axis. Here the x-axis is VDS, because we are considering it as the drain resistance. So that's why we need to consider the output characteristics here. So in the denominator it will be of delta, that is a change in the VDS. So that is your GDS. That is the GDS. So, but in order to solve this, we need to consider the saturation region, and in the saturation region, the current equation of that particular N-channel MOSFET is given as 1 by 2 mu N C naught X into aspect ratio into VGS minus VTH whole square. Since here channel length modulation parameter is given, so we need to add that channel length modulation effect in this particular equation, that is 1 plus lambda VDS. That is 1 plus lambda VDS. 1 plus lambda VDS. Okay. So, but here, what we have to calculate here? We need to calculate the GDS, but how to get this GDS? Just differentiate, just differentiate this ID side, just differentiate this ID side with respect to VDS. So here, the GDS is obtained as, chain, that is the okay, if I consider the normal mathematical operation here, what I have to do is, I need to differentiate ID, I need to differentiate the saturation drain current, or I need to differentiate the drain current in the saturation region with respect to VDS, So if I differentiate this with respect to the VDS, what is the resultant we are going to get? Here, for all this case, for this particular case, we need to differentiate with respect to VDS. So that's why all these values or all these parameters will be treated as the constant. So that's why it will be 1 by 2 mu n C naught x W by L into VGS minus VTH whole square into the differentiation is again only, you're going to get only VDS here. Sorry. Since we are differentiating with respect to VDS, so only the left out part here is going to be lambda. Okay, because the differentiation of this one is constant is 0, so it is going to be the resultant equation. So we know all the values here, 1 by 2 we know that, and here mu naught C naught x is given, W by L is given, the gate to source potential is given, and the threshold voltage is also given, and lambda value is also given. Okay, we just look at this. Mu N C naught x is given, it is 70 into 10 power minus 6 ampere per volt square. W by L is given as 4, and VGS is given as 1.8 volts, and the threshold voltage, that is VTH, it is given as 0.3, that is also given here, and the lambda is also given, that is a channel and modulation parameter, that is 0.09 per volt. If you just substitute all these values by substitution, if you just substitute all the values are given. Okay, substitute the values. So we will get the transconductance, or the, it is a output of the drain conductance, which is equal to 28.35 microsiemens. Okay, make sure that in which unit we have to convert that. Here in the question, it is given that we need to determine the drain conductance in the microsiemens, which means, for example, if in the answer, if you get some 28.3 into 10 to the power of minus 6 joules, you need to convert that into micro. For example, in your calculator, if you got like this, okay, so what I will do is, for example, assume the calculator 2835. Okay, you should not write this one. Okay, you should first convert this answer in terms of microsiemens. That is, you need to convert this in terms of microsiemens. That is 28.35. So you need to enter only this magnitude part. Okay, that is 28.35. So your answer is 28.35 because it is already given in microsiemens. Okay, we need to determine the drain conductance in microsiemens. Okay. Okay, now let's move on to the next question. Here it is again based on the MOS capacitor. This question is based on MOS capacitor. Here for this particular case, here the figure shows the high frequency CV curve of a MOS capacitor at 300 Kelvin with 5 ms. It is a work function of metal semiconductor. Okay, this is a work function between the metal and semiconductor. Here 5 means it's a work function. Okay, this is the work function. Here it is given as the work function between the metal and semiconductor is given as 0, and there are no oxide charges are present here. Okay, there are no oxide charges. And we need to identify here. So what we have to do here is we need to identify the flat band condition, inversion condition, and the accumulation condition from this particular high frequency CV curve. Okay. Basically, if I just draw the capacitance voltage curve here, for high frequency, you're going to get like this. But for low frequency, you're going to get the characteristics like this. Okay, for low frequency, you're going to get the characteristics like this. So this is for low frequency, and this is for high frequency. Okay, here for the high frequency, it is already given by for the high frequency CV curve, which means we need to consider only this portion, this region. Okay, that is given already here. And here it is also mentioned that the work function is given as 0 and there are no offset charges, which means here the flat band voltage will be 0, which means because here there is no work function and there are no offset charges here, because of this, what happens? Because here phi ms is given as 0 and there are no offset charges. There are no offset charges. So with this, what we can do is, you know that the flat band voltage is given as, and again, this is again the quantitative analysis. We need to know this relationship. This is somehow related as work function between the metal and semiconductor minus oxide charges, okay, divided by it's not divided by oxide thickness. Okay, here the oxide charges are 0 and the work function is also 0. So if both these terms are 0, what happens to the flat band voltage? The flat band voltage will be 0, which means at Vg is equal to 0, what it implies is at Vg, at gate potential is equal to 0, you will get the flat band condition. Okay, you will get flat band condition. Which means if you just look at this particular curve, this x-axis is the gate voltage. Okay, this x-axis is the gate voltage, and at this particular voltage, that is at Vg is equal to 0, because at Vg is equal to 0, the flat band voltage is 0, right? So which means here the Q corresponds to the flat band condition. This Q corresponds to the flat band condition, and it is of p-type substrate, because in the p-type substrate, here this is your capacitance. This is having the minimum capacitance, and this is having the maximum capacitance. Why it is a p-type semiconductor? Because in the p-type semiconductor, or p-type substrate, C minimum is going to be the inversion region. This is going to be the inversion region. It is going to be the inversion region. Okay, whereas this region is going to be the accumulation condition. This is going to be the accumulation condition, which means in the accumulation condition, the capacitance will be taking the larger values, and this is going to take the smaller values. Okay, so for the left side portion of this particular flat band voltage, it is the accumulation condition, and for the right side, it is going to be the inversion region. So here, if you just look at this, the flat band is the point Q, and the inversion is point R, and the accumulation condition is at point P. So the answer is QRP. Okay, this is the answer. QRP is the answer. Okay. Now let's move on to the next question. And again, this is the direct question. Here, see this. Here we need to consider a long channel MOSFET with a channel length. Here the channel length is given as 1 micrometer, and the channel width is given as 10 micrometer, and the device parameters are acceptor concentration, that is Na is given. Acceptor concentration Na is given, which is equal to 5 into 10 to the power of 16 atoms per cubic centimeter, and the electron mobility is given μn, and the oxide capacitance per unit area, that is C0x is given. C0x is given, that is 3.45 into 10 power minus 7 farad per centimeter square. And the threshold voltage is also given. So here for this long channel MOSFET, see here for this particular case, Na is given, which means the p-type substrate is given here. Okay, here the substrate is of p-type. Okay, here the substrate is of p-type region because Na is given, Na is given, Na is given. So this implies it is a p-type substrate, p-type substrate. So in which type of the semiconductor you are going to observe the p-type substrate? You are going to observe the p-type substrate in the n-channel MOSFET. Okay, you are going to see the p-type substrate in the n-channel MOSFET. Okay, by default it is a enhancement type. Okay, by default it is of enhancement type because usually the depletion mode devices are not going to be used nowadays. By default, it is of enhancement type. So from this, we need to determine the drain saturation current. So we know that the drain saturation current is given as 1/2 UN C naught X W by L into VGS minus VTH whole square. Here again, here the lambda value is not given. That is the channel length modulation parameter is not given here. So we can assume the ideal case, that is lambda is equal to 0. So this is the corresponding expression. Okay, if they give the channel length modulation parameter, we need to add 1 plus lambda into VDS at this point. Okay, since here the channel length modulation parameter is not given, we can neglect the channel length modulation effect. We can neglect the channel length modulation effect. So this is the corresponding equation for this. So if we just substitute all these values, because we know all the values here, mu1 is given, C naught X is given, W is given, L is given, VGS is given, here VGS is 5 volts. Okay, here VGS is given as 5 volts and threshold voltage is also given. The threshold voltage is 0.7. So here all the values are known here. It is just a simple substitution. If you just substitute all these values by substitution, you will get ID sat is equal to 25.52 milliamperes. 25.52 milliamperes. So here in the question, it is given that we need to determine the drain saturation current for this particular gate voltage in milliamperes, and you should round off that value to 2 decimal places. Okay, so it is 25.52. You need to just write only 25.52 because here already the unit is given. So the answer is 25.52. Don't write 25.52 into 10 to the power of minus 3. Okay, because here already milli is given. So this milli you should not enter here. Okay, you should enter only this value. Okay. Always make sure that the units are proper and correct. Okay, now let's move to the next type of question, which is based on the PN junction type, or it is based on PN junction or a simple diode. Okay, it is a simple diode. In an ideal, it is given that in an ideal PN junction with an ideality factor of 1, it is given that the ideality factor, that is eta, which is equal to 1, and the temperature is given as 300 Kelvin. Temperature is given as 300 Kelvin. And the magnitude of it is given that the magnitude of the reverse bias voltage that is required to reach 75% of its reverse saturation current, that is rounded off to 2 decimals, is dash millivolts, which means here what we have to do is we need to determine the magnitude of the reverse bias voltage. So anyhow, for a PN junction diode, we know that the diode equation is given as ID is equal to I naught, where I naught is the reverse saturation current. It is a diode current. This is the diode current and this is the reverse saturation current. The diode equation is written as ID is equal to I naught into e to the power of the diode voltage divided by ideality factor into thermal voltage minus 1. Here it is given that we need to determine the magnitude of the reverse bias voltage, that is VD. We need to calculate the VD for which the current is equal to 75% of the reverse saturation current. Since we are considering the reverse bias voltage, definitely the reverse current will be minus. It is given that it is going to reach 75% of its reverse saturation current, which means IR is equal to minus, because it is a reverse current, which is equal to minus 0.75 into the reverse saturation current. That is, here this ID will be equal to IR because it is reverse biased now. Okay, it is reverse biased now. So you just simply substitute this minus 0.7 by I naught, which is equal to I naught into e to the power of VD. Here VD means the voltage across the diode. Okay, that should be the reverse voltage that we need to calculate here. So here the voltage across the diode is going to be the reverse voltage. Okay, I just call it as VR divided by eta is given as 1 and the thermal voltage is given as, here the thermal voltage is not given, but here since the temperature is given and K is given and the charge is given, we can calculate the KT by Q is equal to thermal voltage, which is approximately 26 millivolts, right? This is approximately 26 millivolts. If you just substitute all these values, that is 26, and this I naught will cancel out each other, and we just solve this e to the power of VR divided by 26 milli, which is equal to 0.25. Okay, because this if I just shift this minus 1 towards this side, it will be plus 1. 1 minus 0.75 will be 0.25. So if you just solve this is again a simple direct substitution. Okay, here we need to calculate by taking log on both sides, taking log base E on both sides. We will get VR by 26 millivolts is equal to log base E of 0.25. Okay, so this VR is equal to 26 milli into 10 to the power of minus 3 into log base E of 0.25 So what we will get here because of this log of 0.25, we will get some negative value, right? It will be minus 35.82 millivolts, minus 35.82 millivolts. Okay, since here we are considering the reverse bias condition, so that's why we got the negative value. But in the question, what they have asked here, they just asked only the magnitude, right? They just asked only the magnitude of the reverse bias voltage that is required to reach this amount of current, which is rounded off to 2 decimal places in millivolts. Here already it is given that we should write this V reverse bias voltage in millivolts, and we need to write only the magnitude. So what is the magnitude of this particular value? The magnitude is only 35.82 because we should write only in the millivolts. So that's why there is no need to write this milli again here. So the answer is 35.82. So the answer is 35.82. Okay, it is 35.82 millivolts. Okay, and again I'll just give the idea for this problem. You can solve this. Here it is given that the donor concentration is given, that is the donor and acceptor impurities in an abrupt silicon junction diode are given as 1 into 10 power 16 per cubic centimeter and 5 into 10 power 18 per cubic centimeter. That is, the donor concentration is given as Nd is equal to 1 into 10 to the power of 16 atoms per cubic centimeter, and here acceptor concentration is given as 5 into 10 to the power of 18 atoms per cubic centimeter. That is, Na is given as, here Na is given as 5 into 10 to the power of 18 atoms per cubic centimeter. Here I just give the idea here. You can solve this on your own. So here assume that the intrinsic carrier concentration in the silicon is given at this temperature, and the thermal voltage is also given. Here the permittivity of the silicon is also given, that is 1.04 into 10 power minus 12 farad per centimeter. Here, what we have to do is we need to calculate the built-in potential and the depletion width of the diode. We need to calculate the depletion width of the diode under the thermal equilibrium condition. That is under no bias condition. Equilibrium means under under no bias condition, which means don't apply the bias. Okay, no bias condition, no bias. So here what we have to do is one is the built-in potential. We know the built-in potential for the PN junction. That is, what is the built-in potential? Built-in potential is the thermal voltage into ln Na Nd divided by Ni square. Ni square. Here, see here, we need to calculate this one. We know thermal voltage. What is the thermal voltage? It is the thermal voltage. Here, Vt is equal to 26 millivolts. It is given. So you just substitute that one. This is a log by C. Here, Na is given. That is 5 into 10 power 18 per cubic centimeter. And Nd is given. That is 1 into 10 power 16 per cubic centimeter. And here it is also given that the intrinsic concentration of the silicon, that is Ni. Ni is also given. So you just substitute that one. And if you solve that, after substituting all these values, you will get the answer. Please solve this on your own. Okay. So similarly, the next question is we need to determine the depletion width of the diode. So the depletion width is obtained as square root of 2 times the permittivity of the silicon divided by the charge into the built-in potential. See here, first we need to calculate the built-in potential, then we need to calculate the W because it is dependent on VBI into 1 by Na plus 1 by Nd. Here also all the values are known here. Okay. Here, once if we calculate the VBI, we can substitute everything because here epsilon SI is given as 1.404 into 10 power minus 12 farad per centimeter. Farad per centimeter, and Q is given, or if they have not given Q, yes, it will be 1.6 into 10 power minus 19 coulombs. And here VBI that we can calculate from this particular step. And here the acceptor concentration is given and the donor concentration is given. So we can just simply substitute all these values. We can get the depletion width. So this is the way to solve this particular problem. So accordingly, we need to answer the question. Okay. Okay, and I just move on to the next type of the problem. Okay, here see here. Okay, this is the next question. I want to solve this. Okay. So here it is given that an abrupt PN junction that is located at x is equal to 0 is uniformly doped on both the P and N sides, and the width of the depletion region is given as W, and the electric field variation in the x direction is Ex. Which of the following figures represent the electric field profile that is nearer to the PN junction? So we know that if we consider the PN junction, and again this is again based on the Poisson's equation and the PN junction. Okay, here we need to consider the Poisson equation also because we need to calculate the electric field with the help of the potential variation and the charge distribution. Okay, with the help of the charge distribution, we can calculate the potential distribution. With the help of that potential distribution, we can calculate the electric field. That is by E is equal to minus gradient of the potential, we can calculate the electric field. Always this electric field will be positive for this particular case. Let us see how it is possible. If I consider this is the P region and this is the N region. Okay, here because of the diffusion process, and again here also it is not biased here. So under this equilibrium condition, what happens on the inside, the positive charge will be, or the positive ions will be developed, and on the P side, the negative ions will be developed because of the diffusion process. Because of this diffusion process, see here, because of this diffusion process, the static charges will be created at the junction, right? Because of this the diffusion process, the static charges, because these charges are actually not moving. If the charges are at rest, what it creates? If the charges are at rest, what it creates? It creates the static electric field. Creates static electric field. Static electric field. So in which direction the electric field will be pointed here? Always the electric field will be pointed from positive charge to the negative side, negative charge. That is, the electric field will be in this direction. That is from N side to the P side, N side to the P side. Okay. So if you just look at this, the charge distribution will be like this. So if you just calculate the electric field based on the potential gradient, we will get something like a ramp function because of this relationship, because we need to integrate this particular distribution. So among these, we will get this to be wrong, because here the electric field is negative here. Electric field is negative on the N side, but on the N side, we should have positive, right? We should have the positive electric field on the inside. Later on, what happens in the P side, it should decrease. Okay, the electric field is going to be pointed in this direction. So which means at the inside, the electric field should be positive always for this particular case. Among all these options, if you just look at this, in this case, on the inside, the electric field is negative. This is wrong. Here also, on this N side, the electric field is negative. This is not correct. Here, on the inside, the electric field is positive, but actually this is not uniformly. Okay, here it is not taking any ramp function, because we need to integrate this one, right? We need to integrate this charge distribution here, because first we need to calculate the first we need to understand the charge distribution, then we need to get the potential distribution. From this potential distribution, we need to get this particular electric field. So from this, we will get to know this is going to be the correct answer, because we should have some positive value of the electric field, and it should not be like this. Okay, it should have some slope. It should have some linear relationship on the N side as well as on the P side because of this charge distribution. So this is going to be the correct answer, and this is wrong. Okay, I just wind up the session by solving this problem. Look at this. Here, some circuit is given, and again, this is based on the MOSFETs. This is again based on the MOSFETs. Here, we need to assume that the transistors M1 and M2 are identical. What it means is the W by L ratio, all those stuffs are same. Mu n C naught X, W by L of these two transistors remains same. Okay, there is no need to bother about these parameters now. And it is given that the threshold voltage is given as 1 volt, and the state of the transistors, which means we need to identify in which operating region these M1 and M2 are operating. Okay, here see that for this transistor M2, the gate voltage is 2.5 volts, and the drain voltage is 3 volts. Okay, this is the drain and this is the source. Okay, and this is the gate for this particular M2 transistor. So here the drain of this particular transistor is 3 volts. Now if I consider the transistor M1, the gate voltage is 2 volts, and the source. Here we don't know the drain voltage here. We don't know the source voltage. But here the source voltage of the transistor M2 is equal to the drain voltage of the transistor M1. Okay, so that's why I'm just writing this one. That is VS2 is equal to VD1. Now let us find whether any one of the MOSFET is in the cutoff region. Anyhow, it is not given here. If you just look at these particular options, the cutoff region is not at all given, because for all these cases, here VGS is going to be greater than VTH. So this condition will be satisfied by default, because if you just look at this gate voltage and this gate voltage, this is greater than the threshold potential. So it is not in the cutoff. Okay, it is not in the cutoff, which means the diode here, the transistors are conducting. If it is conducting, means then it can either operate either in the linear region, it can either operate in the linear or a triode region. And sometimes for the MOSFET, the linear region is also known as the triode region. And the second operating region that could be possible for this case is the saturation region, or this is saturation region. Okay. Okay, for the saturation, let us consider, let the condition for, okay, when we know that the condition for the saturation region is, condition for saturation is VDS should be greater than VGS minus VTH. Okay, for both the transistors, we need to verify whether this condition is satisfying or not. We need to say, verify whether this condition is satisfying for both the transistors or not. Now let us consider the transistor M2. Here VDS is 3 minus Vs and VGS minus VTH is VG is equal to 2.5 volts minus Vs minus threshold voltage. What is the threshold voltage here? The threshold voltage is given as 1 volt here. It is given as 1 volt. So for the transistor M2 VDS, and let's write VGS minus VTH on the other side here. Now let us verify whether this VDS is greater than VGS minus VTH or not for the saturation region. Here VDS is given as 3 minus the source voltage, but we don't know that source voltage. And here if I consider the gate to source potential here, it will be 2.5 volts minus Vs minus 1. So if you just simplify this, 3 minus Vs is on the right hand side, it should be 1.5 minus Vs. See here, we don't know Vs, anyhow, this is going to take some value. But if you just look at the first term here, this is having the value 3 and this is having the value 3. Definitely this VDS should be greater than VGS minus VTH. Okay, this condition will be satisfied. So what it implies is here M2 is operating in the saturation region. M2 is operating in the saturation region. Now consider, because it is given that both the transistors are identical. Here it is given that both the transistors are identical. Wait for a minute. It is given that both the transistors are identical. We can consider the drain current to be like this, because here mu and C naught x W by L is going to be constant for both the transistors. So what I will do is ID is related like this, VGS minus VTH whole square for transistors, for different transistors. Okay, so now let us assume anyhow this transistor, we don't know the state of the transistor M1. So if you just look at these options, M2 is in the saturation, which means either this option can be correct or this option can be correct. But if this option is completely wrong and this option is completely wrong again, because here M2 should be operated in the saturation region, either A or C can be possible. Now let us consider the M1 is also operating in the saturation region. Assume M1 is operating in the saturation region. If we assume M1 is in the saturation region, if we assume M1 is operating in the saturation region, we can consider the drain current of this particular transistor is, we can neglect the mu and C naught x W by L, because the drain current, that is the current that is flowing through the transistor M2 will be equal to the current flowing through the transistor M1. If I equate both the terms here, what happens? If I consider the drain current for this transistor M2, it will be VGS minus, that is VGS of the transistor 2 minus VTH whole square is equal to VGS of the transistor 1 minus VTH whole square. Okay, so if you just solve this equation, anyhow here, if you just take the square root on both the sides, we can eliminate the square term. And here VTH is also same for both the transistors here, because they are having the same threshold voltage, so we can cancel out that the threshold voltage also. So if you just solve this, you will get VGS2 is equal to VGS1. Now let us solve this. What is this VGS2? VGS2, and this is here VG minus VG1 minus VS1. You just look at this equation now, and you just consider these values. This is for transistor M1 and this is for transistor M2. So what is the VGS value for this transistor M2? VGS is 2.5 minus Vs of the transistor S2 and here this is 2 minus 0 because Vs is 0 here. Okay, so for the transistor M1, it is only 2. Okay, VGS is equal to 2 here. So because this is 0, so this is 2. So VGS 2, VG2 minus VS2 is equal to 2. Now let us consider the VS2 now, because we don't know the value of VS2. So what is the VG2? VG2 is 2.5 volts. 2.5 volts. This is 2.5 volts. So VS2 is equal to 2.5 minus 2, which is equal to 0.5 volts. 0.5 volts. So here the voltage at the source side of the second transistor is obtained as 0.5 volts. So from this, what we can say is, what we can infer is, see here for this particular case, Vs is now if you substitute that Vs is equal to 0.5 in this equation, definitely this condition is going to be satisfied. Anyhow, this M2 is not a problem here. Now let us consider for the transistor M1. For the transistor M1, VDS should be greater than VGS minus VTH. Okay, for this transistor M1, the VDS, what happens to the value VDS here? VD is equal to, for M1, VD, we don't know. What is the value of the drain current or the drain voltage of the transistor M1? For the transistor M1, the drain voltage is equal to the source voltage of the second transistor. But what is the source voltage of the second transistor? That is 0.5, right? So if we just substitute that, 0.5 here, and if we substitute VGS, what happens here? VGS is equal to 2 volts. 2 minus 1 is 1. Whether this VDS is greater than VGS minus VTH, whether 0.5 is greater than 1, definitely it is not possible, which means whatever we assume here is not correct, which means here M1 is assumed as it is operating in the saturation, which means the assumption is wrong here. So whatever we assumed here is wrong. That is, assumption is wrong, which means M1 is not operating in the saturation. Anyhow, it is conducting because the VGS is greater than VTH. Definitely, it should operate in the linear region, which means M2 is in the saturation. M2 is in the saturation, and M1 is in the linear region or the triode region. It is also called as triode region. So from these options, it is not possible again. Option A is not possible. So only the option C is correct. Option C is correct. So this is about the today's session. If you have any doubts, please let me know. And thank you very much. Okay. And this is about today's session on the electronic devices. If you have any doubts, please let me know. Thank you.